Okay, any questions before we get started today? Nothing? Who here started trying to build their GA? Couple people, yeah. Keep them up. I want to get a sense. How many? All right. Of course, it's not due until like 2 weeks, right? So, but I will warn you. Back when I was in 4th year of my undergrad, I was taking a machine learning course, and in that course, like our assignment 1 was to build decision trees. Okay, and this is a time before everyone would just import SciPy and you're all, or scikit-learn and be all ready. So like we were building it from scratch. And building the decision tree actually it's not hard. It's a fairly easier, I mean, I shouldn't say it's easy, but it's not too bad compared to many other sophisticated algorithms. The trouble though was, like, I don't know, we got like 2 weeks for it. And the assignment, like we had to build it, but it's similar to how I'm doing it where, you know, I don't, like, you're a senior student, you can build this. I care more about, like, well, what you did with it, your exploration of it and all that stuff, the write-up. So we had to do a big write-up for it, and we had to do it in LaTeX, where you don't have to, but you're encouraged to with points. And of course I was going to do LaTeX. So, I don't know, I usually never procrastinated. I was always a very good student in university. I was a terrible student in elementary school and high school. I was lucky to get in university. But the trouble was, I don't know, it was like the day before the assignment was due, and I sat down and cranked out the decision tree. It wasn't too hard to do, great. And by this time it was like maybe 4 or 5 p.m. and I was in one of the computer science labs back at my university and had to do the write-up. Okay, great. Had to learn LaTeX, which I knew would be kind of a pain, but whatever, I could figure it out. And this is a time before Overleaf and everything. This is a time when like your basic LaTeX editor was something, like all that we knew of at the time was something that was only slightly better than like Notepad. It was terrible. But that's what we had. I never in my life ever pulled like an all-nighter working on something until that night. The write-up took so long. The write-up was by far the hardest part of it. And I stayed up. I think I finished it at like 11 the next day. Like at 11 a.m. the next morning, I finally like had it done. And I did a terrible job, but it was done. So I wasn't not gonna have it handed in. I think it was due at like 11:55, and we had class that day at like, I don't know, like sometime in the afternoon. So I submitted it, I went home, I went to sleep, got up, went back to school. And during the lecture, because like, I was like the only one who finished it, because every other student in the room was like, oh, the write-up was harder, LaTeX hard, so the prof was like, oh, okay, I'll give you an extension. And I was like, no! I remember like standing up and being like, no fucking way! Like I lost it, right? And I didn't care. There was a room of probably, I don't know, the class was probably smaller than this, maybe 20, 30 students. And there's everyone looking at me like, well, fuck this guy. But I'm like, you know, it's a small group, we all know each other pretty well. And I made my case, I'm like, this is bullshit. I stayed up all night, I got it done, and then the compromise that was made was, in that course, the late rule was it's in on time, or if it's after by a couple of days, you lose like 25% of your final, like you can't get 25%. The max grade you can get is 75. So the compromise was I'll get 12.5% bonus, and everyone else only loses 12.5%. And I was okay with that. No lates! No lates. If I could do it, you can do it. So just be warned, but also be warned that the write-up is going to be perhaps more difficult than you realize. Not hard, but time-consuming. If you're doing LaTeX, which I highly recommend, there's a bit of a learning curve, but once you get used to it, it's actually glorious, and you might end up not choosing to use anything else because it's great. Has anyone used it before? 1.5, 2, 2, wonderful, perfect. For you, everyone else, use it. It's great. And overleaf is fantastic. There's some instructions in the assignment. Someone came to office hours today asking a great question. And I'm going to point you out as you. You came to office hours asking a great question of like, okay, I build a GA, but here's an idea. What if I try like this? My answer to that question is always going to be, try it. Even if it's a bad idea, try it. Even if you were to tell me, and I knew that other people tried it and it was a terrible idea, I still want you to try it, because the point of this stuff is to play around, try things. This isn't like you're learning to program. You can all program. This is more of a science course than a imagine this was another course where I told you to pick up your pencil and paper and just start writing crap, right? Like, well, no, that's silly. It's not about the programming, it's about exploring, it's about trying all these things. I'll give you the framework, but yeah, I just feel like it just got darker in here. All right. Any questions though before we start playing around with the GA? Okay, what I thought would be good to do today is just hack around with the genetic algorithm and see how changing the values will affect the performance and the behavior of the algorithm. Remember, this is a very simple problem. It's just optimizing the binary string of zeros and ones to be all ones. But let's start with, I know last time we kind of did it. For those at the back, can you see this reasonably well? Yeah, cool. So here are, I'll just zoom in a little more. Here are the key values here that really I'm going to want to play with. Population size, chromosome length, generation. Chromosome length, really that will be problem dependent, so this value here is more how hard am I making the problem. So it doesn't so much affect the GA, it affects the problem, which then will affect the GA, just FYI. But we have population size, which I actually want to make a little smaller. Number of generations, how big our selection pool is, crossover rate, and mutation rate. The values I have for crossover and mutation, if I start writing my GA, those values are almost always where I start them before I might try to change them a little to see how it affects the runs. So here we go. And also warning, if you start doing this with your TSP, and you start running it on very large problem instances where there's 1,000 cities, expect to have insanely large settings, expect to hit run, and expect to come back hours later. That's normal. If you hit run and it's hanging, you're like, oh no, it froze. No, probably not. It's probably running. It's just, these are big problems. So, simple. Let's hit run. Okay, there we go. What did we get? So, look, the best result we got at the end wasn't even the best possible result there. Of 32 zeros and ones, I only got 31. But we got there. When we started, presumably on average, there were 16 ones in those populations, right? Because I just randomly picked 0 and 1. In fact, look at that. On average, there was 16. Wonderful. But over time, we can see how the best changes on the average population as well. In fact, when I look here, any idea, based on what you know, and this is a tough question. I don't necessarily expect you to have an answer for this. But based on what you know so far, I don't know, what do you think kind of happened there? And there was that little bump at the end. If I hit run only to 80, I kind of would have been stuck, eh? So, what do you think happened? What do you say?
Was it caught in a local optima and then it mutated out of it?
I'm betting that's what happened. I'm betting that, the population size is very small here. It's 10. So it probably, the population was probably fairly not diverse, fairly similar. So things like crossover don't really have that much of a change. But I'm guessing at that point, maybe we got a lucky mutation that just added enough diversity to then spice things up a bit. Wonder what'll happen if at any point I hit run. If you think of anything, if you have a question, raise your hand. But okay, I'm gonna hit run again with the same settings. You know, did we actually get the best result this time? No, look at that. How about that? Just to warn you, if I wanted to hit run, hey, look at this. We got kind of like stuck there, and I don't know, maybe kind of got stuck here. Looks like we jumped a couple there. If you're ever, because this is like a random process, there's a lot of randomness involved. Every time I hit run, I'll get slightly different results. If you want to like talk about how good your algorithm is in general, you're never allowed to just hit run, get results, and then make some changes and hit run and be like, oh, this one did better. Well, it did better once, but if you keep hitting run, you might start getting a whole bunch of different answers. What we care about is, so you might say, okay, well, I'll hit run a bunch of times, which you should. In computer science, any statisticians in here? You took, well, I don't know if you really would have covered it in like intro stats. Raise your hand if you've taken more than just intro stats. Okay, a few. I'm gonna say something that might anger you, but in computer science, you gotta have at least 30 runs. Otherwise, no one will take you seriously. If you're a statistician, you probably were just like, oh my God, only 30. But yeah, we do 30. So you gotta have at least 30 runs, and every time you hit run, you'll get a slightly different result, right? So if you wanted to plot your results, let's say, I'm just gonna do like a histogram. If I'm plotting my results, and this is like fitness, where, I don't know, maybe 0 is better because it's like TSP. Every time I hit run, I'll get like different permutations with a different fitness value at the end. You'll end up with a distribution. I don't know, maybe it looks like that. It's kind of hard to see. I'll change markers. You'll end up with a distribution, maybe it looks like that. And then maybe I change some settings and I hit run again. And I don't know, maybe my distribution looks more like this, right? So I'll have two different distributions of results. And what I really want to do to compare these algorithms is compare the distributions. Raise your hand if you remember from baby statistics how to compare distributions. Oh no, that's okay. I will spend some time later in the course talking about like permutation tests, which is the best way to do this, I'd say. But raise your hand if you've heard of a t-test before. A t-test is, like, just do a t-test. That'll make me happy. Whatever you do, never go, well, on average, this is better than that. No. Because on average, this one's probably better. But if I ran the red one a bunch more times, the distribution might change its shape a little bit. Similarly with the green one, for all I know, they might actually, like the shape of these distributions might actually be so similar that really at the end of the day, they're the same. Yeah?
Should we be, is 30 just kind of like a convention, 30 runs, or like would statistical power be like a waste of time to calculate?
It wouldn't be a waste of time to calculate, but like, as a quick and dirty rule of thumb for new programmers who, like yourselves, aren't that stats literate at this point, and I don't mean that in a negative way, it's just you haven't had that familiarity because you've been taking computer science courses or something. 30 is like, just do 30 and then do the comparison. Realistically, if I'm ever doing something, I'm gonna do at least 100 just because I like it better. We are a little lucky too, like in stats, what your n should be really will depend on a bunch of different things. One excuse computer scientists will make is like, well, sure it's random, but we do, like compared to like observing real things, the amount of possible noise is a lot smaller in our data because it's very controlled, because we're running it on our computers and all that, so we can get away with the smaller n. But 30, you're good to go. 29, oh, I don't know about you. So, yeah, anyways, just warning on that. And look at this cool marker, it's double-ended. It's really cool. All right. Let's make this problem, okay, population size is really small. Let's make it 100. Let's double it. And now I'll hit run again. Look at that. We got the best answer. All ones, you can see it peeking out at the bottom. Anything you notice about the shape of this curve? What? I don't know what that means. Use your words.
It hits the optimal solution pretty early.
It hits it earlier, that's for sure. But maybe that was a fluke. Let's try again. No, it definitely looks like, I mean, at least for the 2 runs. This one maybe a little later than the others, but we can see that it gets to good solutions. Ooh, this one's a little different. Now it looks like maybe that's not true. Well, now this is true. But yeah, did I see your hand up?
Yeah, I was gonna say it skews left.
It skews left?
Or should I flip it?
Well, but skews usually when you're talking about the distribution, right?
Right.
Yeah, whatever. All right, so let's make this problem harder. 32 is small. So now let's double how hard it is. And we'll hit run. All right, in the end, I can see that we didn't get the optimal. We got 2 zeros in there. And look at the shape of that curve. Let's try it again. Oh, look, this time it looks like we got the optimum. Oh no, we didn't. All right, so it's doing okay. What do you think will happen? So selection size, this is where I basically pick some subset of the population and take the best one of that as one of the parents. And then I do it again. So I have it set to 2 here. I pick 2, take the best one. What do you think will happen if I make it pick 1? So it's basically just randomly pick 1. Take a second, don't answer, just take a second and think about what you think that would do to the results. Raise your hand if you're like, yeah, I got an idea. Do you need more time, or are you just that confused? Do you need more time to think about it? No? So raise your hand if you just have no idea. Well, let's see. Weirdly, it actually got worse on average, which is hopefully atypical. It's kind of just going sideways. You got a question?
I was just gonna make a comment.
What's your comment?
Wouldn't it make sense that it's doing worse? Because effectively, if you have a selection size of 1 and it's completely random, and your population size is 20, which, I mean, if it was even higher, it'd be even worse. You have a 1 in 20 chance of selecting the good one, per se.
Yeah. Here, we've eliminated selection pressure. By only selecting 1, we've kind of turned it more into a random search. There's nothing really encouraging the good ones to be, the relatively good ones to be selected. Even with 2, we were left with, we were getting good results with 2, but 1, it was absolute trash. So, I don't know, what if we make it 4? What do you think?
Just gonna get stuck in a local optima too early.
Interesting. Well, in this scenario, we got the best one. Maybe we got lucky. We didn't quite get the best. And you can see some levels of stagnation there. Well, with that fun idea, let's make it 6. Let's see if we can actually find what you were looking for, because I have a feeling that exactly will happen eventually. Well, not yet. We'll come back to this idea when we make the problem harder. Because now just random chance, we can get lucky. I mean, if I make it 20, this is absolutely going to be, well, it still worked. We're getting lucky with our mutation, I guess. Let's see what happens if we do this without any mutation. Let's try it again. Let's see what happens. Now, I mean, this is an extreme case. Now, take a second and think about why this is happening. Taking the time to get an intuition about this is going to make evolutionary computation a lot easier for you. Raise your hand if you think you have an idea. Really high, I want to see. Good. So here's why. It'll quickly converge to something. And when it's converged, first, notice the average population and the best end up matching at like generation 20-ish, right? I don't really know, without going in and looking at what each is every time, I don't really know. But I strongly suspect at generation 20, all chromosomes effectively were the same. Because because my selection size was 20, I looked at all of them and always picked the best one. And the best ones were definitely a local optimum. And I mean, if the best one ends up kind of taking over, which will happen with that kind of selection pressure, it'll take over. But there's no way to add any diversity anymore to this when that population stagnates like this. When the population becomes like zero diversity. Because, think about this. If I have a series of 1, 0, 1, 1, 0, 1, 1, and another chromosome that is exactly the same. If I don't have mutation, tell me which index I could pick here to do chromosome to end up with a chromosome that's different than the parents. Raise your hand if that's too hard to see. All right, well, that's good then. What's the answer? There isn't one. No matter where I do the crossover, when they're identical, there's no way to add any diversity just through crossover. Because if I start swapping at the beginning, well, I mean, that's obvious. Start swapping here, oh, they're the same. They're the same, they're the same. Like, there's nothing I can do. So that's why here, we quickly converge to a local optimum because we're always just picking the best one all the time. We're always just basically picking the best one again, mutating them, and putting them in the new population. Any idea why?
How does it get out of the plateau? Like from generation 5 to like 19, like what wouldn't it just like stick with that local optima? Like wouldn't you need mutation to escape that?
Well, at the beginning, they're all random. There's differences at the beginning. Let's think about what happens. At the very beginning, I've got a population, and they're diverse, okay? But there's still a best one. So I'll pick the best one, and maybe I get lucky. Maybe I get lucky, and there is another chromosome that has the exact same fitness, but has a different series of zeros and ones. That can happen. So maybe we have ability of picking not only the best one, but the best ones, but they might be like matched. So, but then wouldn't I always pick the first one? If I'm always, no, because I'm randomly selecting 12. Oh, wait a minute. No, I was lying to you. When I picked, based on how I implemented, you know what it is?
You're only crossing over 16 of them, so there's 4 that are left. And then when you get to that like last 60, or when you pass 16 iterations, like 16 in the normal, and then you get 4, if you throw that randomness back in, and it jumps up.
So that's one of the things, is absolutely 80% crossover. There's a chance that we select the parents and they don't change at all, and then there's a chance that we select the parents and they do change. But the big one is, look how I did selection. Randomly select an integer between 0 and 20 or 19. There's nothing stopping me from picking like 0, 0, 0, 0, 0, 0, right? Which might not actually be the best one. It'd be unlikely, but that's that. So, I don't know, for fun, let's crank the selection size up to like 200 and see what happens. I'm gonna randomly select 200 integers and always check which one's the best. Obviously, this is very excessive, but hopefully as I make this number bigger, I'm always gonna pick the best one. So it's that much worse. So I guess we were getting a little bit lucky before from the randomness. Yay. At the end of the day though, don't do that. That's bad. You don't want these types of results. They're terrible. So, okay, let's go back to 200, but let's add some mutation and see what happens. Huh. Keeping your selection pressure and your like exploration, your diversity balanced is a good thing. But as long as you have both, we can get somewhere. This is definitely much closer to a random search too. All right, let's go back to something reasonable for population size 20. Okay, let's make the problem harder. 128. So now the problem's getting sufficiently difficult that, I don't know, maybe I'll make this 2, population size, let's go back to 10. And let's see now. Okay, so we definitely aren't at the optimum, but that curve looks pretty good to me. Like it's learning the whole way. So, I don't know, if I look at something like this, and let's pretend it's TSP, and I don't know what the optimum is. But if I see a curve like this, one of my first thoughts would be, I'm willing to bet this hasn't converged yet, and maybe I can run it for more generations. And maybe I'll get better results then. So here's what I'll do. Let's see. Let's make the number of generations 200. Okay, looks pretty good. But again, we can see that that curve is still going up. Like maybe it has converged. I mean, we can see that we're actually pretty close to the optimum. But I gave it longer to run. So I would look at this and go, okay, maybe I should let it run a little longer. Let's make it 500 now. All right, there we go. But if in fact, it's not the best solution. Let's make it 1,000 now. Okay, I would look at this and go, okay, I have a feeling I've converged. I don't really know. If this is like TSP and I don't know what the best solution is, I don't really know, because I could hit run, and I don't know, maybe if I ran it for 1,001 generations, it would have bumped up again, right? You don't really know. But before, I had a really strong feeling that I could have let it run longer. Maybe I should let it run longer, I don't know. So there we go, we see a nice curve. I look at this, I'm pretty happy. I wonder what happens now Let's make the population size 20. What do you think this is going to cause? Are we going to get better performance or worse performance? Or just different performance? Let's see. Looks like the bigger population there actually really improved our results. In fact, I don't know, definitely looks like we got the optimum now. Let's see what happens if I make it 50. Okay, I think it improved it some more, but definitely not as drastically as going from 10 to 20. So maybe there's some diminishing returns here. Let's test that theory out and make this 100. Of course, it takes a little longer to run because now I have to do that much more evaluation. Okay, so we're definitely, looks like generation 200, we're finding the best result. And it looks like we're making that curve more aggressive this shape. But yeah, there's maybe some diminishing returns there. So I could get away with maybe 50, but knowing that, I could probably get away with 500 here. Let's see. Oop. Close the plot. Ah, there we go, look at that. I like that. I mean, there's nothing wrong with letting it run forever, coming back 2 days from now, and just hoping I get that much better of a solution if my goal is to find a damn good solution. But if I'm really worried about my poor computer, maybe yeah?
Is there a tipping point with population size where it just becomes so crowded with like randomness, or will it always just find the optimum?
That's a very interesting question. Let's see what happens if we make this just hilariously big. Let's make it like 500. Because all of these changes have different pressures on how it will affect. Maybe in this scenario, given the nature of the problem, it won't have that much of a, okay, cool. It actually converged very quickly. I think if we had a different problem that was a little bit more complex, like if we make this 256, and make this 500, let's see what happens now. All that matters, so if I make the population bigger, but I leave the selection pool the same size, I am affecting the selection pressure, right? Because when I'm picking, I don't know, it looks pretty similar to me, but when I'm picking, if I have a population size of 20, and I'm randomly picking 2 to pick from, versus a population size of 500, and I'm randomly picking 2, which one might be more likely to pick a relatively good one in that size of 20 versus 2 out of 500, right? So it has that consequence. Let's go back to 50. All right, now let's see what happens. Okay, I'm gonna hit run again so we have in our senses of what this looks like. Okay, cool. So there's our curve, but now we're solving 256. So that's why the curve looks a little more gradual. So that's with 2. If we go back to 1, it's gonna be just garbage. Yeah, it's just all over the place. It's funny that the best ones get worse, but can you take a second and think about why that might happen? It seems as if it's like being pulled towards the average, I guess. Does that kind of make sense, I wonder? we're just randomly like on average, each chromosome is just like, each chromosome on average will have 50% zeros and 50% ones. But maybe the top one at the very beginning just has a disproportionately large number of ones. But if it starts being crossed over with just randomly selected ones, it's going to maybe kind of get pulled towards that averageness, right? Because it's being crossed over with one that has like 50-50, and then the next time 50-50, and then the next time 50-50. So it's kind of got this like pull towards average, which is interesting. Okay, let's make this 5 now. It was 2, no, let's go back to 2, see what the curve looks like, and then go to 5. All right, looks good. And it looks like we got, oh, not quite the best result, but a pretty darn good result. Make it 5. Okay. Now it looks like maybe that was a good idea. You know, we turned up the selection pressure a little bit. But, you know, while turning up the selection pressure, what happens if we turn up the, like, mutation, which is great for diversity? Oh, look at that. Is that better or worse than the last one? I can't really remember, to be honest. All of these values have what we call like a non-linear effect on one another. You can't, all those values, think of them all as a bunch of dials that you could turn, okay? I mean, that's effectively what they are. I'm just trying to get you to visualize them as, you have this control panel with 1, 2, 3, 4, 5 dials, okay? You can't, this will never work. You can't pick the one dial and spend time looking for the optimal value, then move to the next dial and look for the optimal, and then the next dial and look for the optimal, and so on. Because as soon as you change one of those dials, it will affect what the best could be for another dial. They are very related to one another. It's not just this linear combination of finding the best values. It is, well, when I change this, right, it causes the algorithm to go like that, but then, you know, if you do that, I would have had to have done this to counteract some of the potential negative incorporated there, but then obviously we would need more generations. It is not possible to just sit down and just find that best configuration of parameters. That's a fool's errand. It's not going to work. There are some systematic strategies we go for. There are some evolutionary computation people where if you're really focused on your algorithm, you might spend a lot of time doing a lot of knob tuning and finding that really good solution. If you're a very applied person that's taking it and you're like, you know what, I just want a damn good solution. I'll find a configuration that gives me good solutions, and I'm like, all right, good. If someone comes and asks, is that the best configuration? I'll say, probably not. But it took me like 5 days to get a result, and I'm happy with the result, so you know what? I'm okay. It all depends. Like, we could keep playing this game for a very long time. So let's make it 1024 to actually make it a rather difficult problem. Let's go back to 100, population size 10, selection size 5, yeah. All right. So clearly, I look at this curve and go, okay, there's a lot more learning to go. And a population size of 10 and generation of 100 for a GA is like very low. Very, 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 very low. Like when I was doing TSP, it could have been like population size 1,000, generation 1 million or something. It would take a while, but you know, I was getting good results. So that's 100. Let's make it 1,000 now and 100. See what happens. Now it's going to take a little while. Like the runtime, I guess in theory, kind of will have scaled up to about 100 times as slow because I made the generations 10 times more and the population size 10 times more. see what we're gonna get. This is one of the things I love about machine learning. When you have algorithms that take a little while to run, you're always like, okay, come on, woo, looks pretty good. Pretty happy with that. Does anyone see any zeros? I don't. Look at that. We solved this rather complicated problem. Well, in relative to the problem itself, which is just finding a bunch of ones. But trying to get 10, 24 ones is pretty tough, right? Let's make it 2048. Oh. Now this should be real tough. It'll take a while. Yeah.
Could you have like layers of GAs like optimizing each other, like exploring the search space of the parameters for
It's like
the original GA and then doing it again?
It's like meta evolutionary computation, and people will do that. There is such thing as like, okay, you've got your GA. Then you have another GA that's tuning the parameters for the GA. And sometimes like you can have it so the parameters are being tuned in real time. I set the parameters here and hit run. But there's nothing saying that over time, maybe I should crank up mutation rate and turn down crossover or something. Maybe that's a really good idea. Maybe make the populations bigger or smaller, see how it affects evolution. There are ideas where people will do in evolutionary computation like catastrophic event. Like there's a big, look at that. We definitely didn't get the best answer. I see at least a couple zeros in there. Huh. They will have like mass extinctions where your population of size 1,000, every once in a while, you just like obliterate it down to like 20. And then over time, maybe let it go back to 1,000 and just see how that affects the results. Because maybe what it'll do is it'll force those that, you know, maybe aren't good in certain areas to die out, and those that are better in other areas can come back, and maybe it can, there's a lot that can happen. All of those ideas, this is what I mean about the creativity in the context of evolutionary computation. What happens if I just like obliterate the population halfway through, keep a couple of them, and just see what happens? Yes, do that. What happens if, like mutation rate gets cranked up, and this changes, and selection pressure changes? Those are all great ideas. Get as creative as you want. I don't even care how bad of an idea it is. If it's at least somewhat possibly conceivable that it might have an effect, do it. See what happens. I'll be very happy if you do that. Okay. Is this getting old or are we having fun? Yeah.
So what's the difference between the red and blue lines?
The red and blue?
Yes.
So the blue is the best one in the population, and the red-orange one is the average fitness of the whole population. So at this scale, it's hard to see the difference. Let's see if I can. Here, it looks like the population is tracking the max pretty well. But you may have saw in some previous examples, they seemed a little bit more further apart. That's what that is. There was one. Okay, right. So now, shoot. Okay, I'm gonna go back to 1024. I'm gonna show you one last thing because I'm getting the sense. Raise your hand if you're like, yeah, I get it. Move on. Okay, I'm gonna do one more thing. Okay, but that value is probably fine. I'm gonna hit run. This will take a second. So here's what I'm gonna do. We were using the fitness function of count the zeros or count the ones to optimize this. Okay? So what I'm doing now is I'm hitting run with that same configuration, and I'm going to, we're gonna look at what the curve looks like. And then what I'm gonna do is run it again, but I'm gonna switch up the fitness function to the other one of well, what does it mean in binary? Optimize what the value is in binary. That's what the fitness will be. So there, that's what we're looking at here. Maybe I should save that. Okay, and now down here, what did I call it? Fitness int value. Perfect. So now, all right, I'm gonna hit run again. Oh no! What did we do wrong? Fitness max. What? Anyone have any idea what this could possibly mean? It's for the average fitness. Average. D-type? Okay. Whatever. In that case, let's just ignore the average. All right. So now, changing the fitness function looks like it might actually have a bit of a consequence on the runtime. Shoot. Okay, it's not too bad. We'll let it run. And I'm curious, maybe the changing of this fitness function, because remember the consequence of this fitness function here, is it's kind of shifting the emphasis of where the search matters, I guess, for the algorithm from the genotype space to the phenotype space, right? The zeros and ones was like, well, okay, we know in the genotype space all ones is good, and we know how, like, we can move through that. Same over here, but we saw how, like, well, you know, a small change there can have a huge change here, and a small change there could also have a small change here. Where here, small changes are all like kind of like consistent in what they could mean. It's like one step forward, one step back. So I'm curious how, what kind of effect this will have. I mean, while we're waiting, does anyone have any other questions? And note that this type of just like tinkering, you might like get used to it a little bit, because there is a lot of this tinkering, a lot of this knob turning in this area. Oh, no. Oh, I see the problem. I've got 10, 24 zeros and ones. What's the biggest integer that could represent? What's 2 to the 1024? All right, we got a problem. That's a terrible idea. Looks like we've got a similar solution, I guess. Shoot, I realize we're running out of time, but I kind of really wanted to show us this. 128. What's 2 to the 128? Shoot, no, we should probably do 64. Nah, because then that's going to be 63. Because computer's going to assume it's a signed bit. And here's hoping that Python is happily running with 64 bits. Raise your hand if you know why I'm concerned about this. Okay, don't worry about it. Okay. All right, this should run quick. Okay, this is with the int version of the fitness function. Crap. All right, well, I spoiled all the fun, but it will have an effect. Maybe very beginning tomorrow, we'll go back to the small examples and show where it happens. For those of you wondering why I was worried about 2 to the 64, is because 64-bit computer, you can only ever represent unless you are getting fancy. But an integer, the biggest unsigned integer is 2 to the power of 64, right? Minus 1, because 0 is included. If it's a signed integer, it's even worse, because half of the numbers are above 0 and the other half are below 0. So it'd be like 2 to the 23, but that doesn't matter for this class. Anyways, hopefully you didn't think that was too boring.